All right, great. So I guess let's continue from this morning. So this part hopefully will be more pictures and less technical and also more applied. So what I talked to you about is basically one way to overcome the impossibility of randomness extraction is to have used seeded constructions. So here we kind of have various constructions starting from universal hash functions to log-wise epsilon independence to some kind of combination which I didn't talk, which basically the objective was to minimize the entropy loss. So this is kind of one way to do it. But one question is, OK, great. So we have these seeded constructions. So the first question is, OK, let's go back to the design pseudorandom generators. Let's say that will be used inside various operating systems. Can we do it? So one answer is yes. Actually, in our original paper at that time, this was a predominant way to overcome impossibility results. So in our CCS 2013 paper, where we attack Linux, we actually formally defined the entropy accumulation problem. We basically introduced, and if we have time at the end, I'll give you some kind of definition or a definition of this thing. But for now, we're keeping it high level. Basically, we introduce a problem of entropy accumulation, and in our solution, in addition to attacking Linux and Sol, in our solution we have, our construction of PRNG with input was, which converts the entropy sources to repeated randomness. It uses a seed, right? And it uses leftover hash lemma and more kind of things over there. But the real answer, that was kind of a theoretical, maybe prototype. The real answer is not really. We cannot, or existing PRNGs are not built based on seeded extractors, and there are two reasons for that. The first reason is the chicken and egg problem. Well, for PRNG, yeah, maybe for the problem of key derivation, maybe it's reasonable, somebody trusted, produce some good public randomness or some public parameters, and you do it. But for PRNG, you just have like a computer, you need randomness. So you need randomness, public or not, to derive some other randomness. So it's a little bit of a chicken and egg problem, even though you can say maybe, I don't know, Intel at initialization will, I don't know, hardwire something. So, I mean, there is some theoretical thing, but you can say maybe it's not a real problem, but the real problem is here. And the real problem is that the source must be independent of the seeds. In all those kind of seeded construction, there was a implicit assumption that the distribution from which we extracted is independent of the seed. And once this assumption is gone, it's very easy to see that all the impossibility results come back. So, this is maybe unrealistic for real PRNGs because eventually the attacker has control over the timing of interrupts and so on. So to assume that that public seed is never known to the attacker, it's kind of bad. And this is the real problem. If you talk to like people like Jason Donenfeld from Linux and so on, people who design like Windows RNG and so on, the real reasons they will totally freak out to use this leftover hash lemma techniques, at least directly in the design of real-world pseudorandom generators, because the failure is basically catastrophic if this assumption is false. So basically, if some whose attacker can control interrupts and so on, they're based on this construction like AX plus B, they're like pairwise independent hash functions. So once you actually break these assumptions, you can just fix the output of the PRNG to 0. You can do anything you want, basically, because there is no cryptography left. And if you remember when I talked about real PRNGs, they all use cryptographic hash functions somewhere, right? Because there's a philosophy was even if some of the assumptions don't work, somehow the failure is not catastrophic. So you cannot like catastrophically break PRNG, and we'll see a little bit when I go forward with it. But for information theoretic thing, yes, this assumption is really strong. If it doesn't hold, the PRNG thing is like completely broken in the worst way possible. So in reality, nobody will use it. So we have to look at something else. And in particular, this is going to start to look much closer to practice. So what people use in practice, they actually will go back to the random oracle model. Remember, I talked about this random oracle, entropy loss 0, and so on. So they will go back to this model. But you will see, even with random oracle, the problem is not trivial. But let's start slowly. So this is going to be our second way to overcome the construction. So one thing, a nice thing about it, it's seedless. So you don't need to create some kind of seed which is independent of the source. And we think that this solution of using cryptographic functions work in practice. But on the downside, the analysis will have to be done in some idealized model, like a random permutation model, random oracle model, ideal cipher model, something like that. All right. So let's keep going. So let's start with a toy example. So it's kind of folklore, even though we only kind of formalized something like that in 2004, but it was well known. So let's look at the So what is a folklore extractor? It's just a random oracle. So assume I have a random oracle, and my extractor is just random oracle G applied to X. And the claim is G of X is indistinguishable from uniform, right? No distinguisher can tell it apart. And I assume that the distinguisher has bounded number of queries to the random oracle. And I claim that for any source of mean entropy gamma, I'm in good shape. And indeed, it's pretty trivial to see that unless the attacker queries random oracle on X, it's just, the output is truly random. So the only way for the attacker to even sniff breaking our PRNG is to query random oracle on X. But he has only Q queries. X has mean entropy gamma, so each query is unpredictable to the attacker as well. So it will only query this probability 2 to the minus gamma. By union bound, we get this kind of security, right? So this is a folklore analysis, and this is where we eventually, using something like that, which I'm not writing, we eventually got our entropy loss 0 kind of thing and so on, if you translate it later. So the question is, have we done? And looking at it in a little bit more detail, the answer is we're actually not done. And so the assumptions that we used in the CD design also kind of implicitly is used here. And the implicit assumption is we assume that this distribution X is independent of the random oracle. And this is problematic both from theory and practice, because from theory it just means, instead of using like a pairwise independent hash function, like a compact representation of the seed or something like that, I'm using an exponential truly random function as my seed. So that kind of totally trivializes the problem. It's like, so a random function is a good extractor or something like that. So, we can get a better bound because we give the attacker more fine-grained access to it, so it cannot read the whole thing. But basically, from a theoretical perspective, it's uninteresting because the seed is exponential. And from a practical perspective, it's also a little bit unrealistic, because if you think about it, PRNG outputs, they affect the timing of interrupts, right? The PRNG also runs on the computer. It also generates some interrupts. So there is some kind of dependency. So we'd like to produce something better, right? So this is maybe a good start. It gives us a great bound, but we would like to use something better. So let's try to do something better. Is it clear what I'm doing? So I'm just starting with a toy thing. I call it Oracle independent sources. And what we're going to try to do, we're going to try to define the problem of random oracle-based extraction in a more realistic model, which hopefully could be applicable to practice. And we call it Oracle dependent sources. So we need to formalize the problem. What does it mean that the source can depend on the random oracle? So one idea, we can say, let the attacker with oracle access choose high entropy distribution. So you can imagine there is our attacker. It has access to the random oracle. And rather than assuming that X comes externally and has this mean entropy gamma, I assume that the attacker, somehow depending on these queries, will output a sample X with some kind of entropy gamma. And of course, if you look at it at this point, so just before you start to saying what are you talking about, we'll see. We'll have to fix it. It's not yet the final thing. Well, in particular, if you do it like that, okay, great. We have a game, but this game is meaningless, right? Because I claim that you cannot have security in this game because, the attacker knows X, right? So obviously, the attacker can distinguish it from random. The attacker just before calling X just calls G of X, and you're done, right? So this is but intuitively, we would like to model the fact that nature selects X, so there is some kind of entropy in the source. Despite this, so the first fix, let's try to kind of fix it slowly. So the first fix would be, we assume that, the nature attacker basically has a split personality. It plays two roles. On the other hand, it plays the roles of nature to sample the source, but at some point it has some amnesia, and it forgets something. So basically, the attacker outputs X, and at the time it outputs X, it has to forget something. So it has a state sigma, and now we'll say that condition on sigma, X has mean entropy gamma. So the attacker produced X and somehow immediately is forced to forget something and has entropy gamma. So that would be the first way to prevent the most obvious attack. So now, once it forgets gamma, the challenger will call this. So maybe the attacker cannot call. So at least it doesn't look that trivial, but unfortunately, it also doesn't make sense if you look at it in a little bit more detail. We have the following attacks. The next attack would be that, let's say the attacker doesn't even make any queries. The attacker will say, my source is G of 0, right? So, so it makes basically a query G of 0, and that's the source. So X is equal G of 0. And because random oracle is random, the attacker doesn't keep any state. It just forgets everything. It just calls G of 0, gives it to the challenger, and forgets everything, the state. So because it's a random oracle, X still has entropy condition G of 0, but then, of course, later the attacker says, okay, I don't have to forget. I'll call random oracle again. I get G of 0 and distinguish it from random, okay? So this also doesn't work. In the full slides, when I gave the talk about only this part, I had like another fix. There is some cool attack, which was like the hardest attack to fix. It's called Extractor fixing attack. But here, let me actually, in the interest of time, I will actually tell you the right solution right away. Yeah.
I have some issues understanding the problem here. So X is just a distribution, or is it like a fixed big string? It's a distribution.
Well, it's a random experiment. So the attacker has coins. So we assume that the challenger has some internal coins. But in this particular thing, the challenger doesn't use any coins. It just calls random oracle on 0 and just outputs it.
No, my question is X. The way you model it, like the way I see it is like it's a distribution.
It's a distribution, yeah. It's a distribution over the coins of the attacker, in which case there are no coins, and the random oracle, because it's random, yeah. So in this case, the distribution, yeah, it's uniform.
And then the challenger, what the challenger would do is sample bit string like lowercase x.
Well, it gets x, it doesn't sample it, it gets it from the attacker, then it calls g of x, and then it flips a bit and either gives the attacker g of x or uniform string, and asks the attacker to tell it apart.
What I mean is that let's assume that x is the uniform distribution, for instance.
Well, I mean, x is produced by the attacker, right? So the attacker produces x.
Yeah. So let's assume that an attacker gives the uniform distribution to a challenger.
Right.
Then the challenger would just like sample uniformly random bit string, and then the adversary would have no.
The challenger is deterministic. Okay, the challenger here, yeah, sorry, you're right, yeah. The challenger samples. Basically flips a bit b, 0, 1. If b is 0, it just gives g of x to the attacker. If b is 1, it samples a fresh independent strings and give it to the attacker, yeah. And the attacker's goal is to guess which one.
So that I got. What I fail to understand is why it is a problem if, let's say, the adversary does not forget some part of its state. Yeah. Because if the adversary gives like a distribution that has very high entropy, then...
Yeah, because like, for example, here, the attacker clearly will win the game, right? The attacker, if the attacker doesn't forget x, is not forced to forget x, the attacker, for example, chooses random x or whatever, like perfect x, truly uniform, doesn't forget it, gives it to the challenger. Obviously, when he gets the challenge, he can win the game. He will call g of x himself and he says, oh, I see if it's really g of x or u, right? So the attacker can tell it. So our goal, remember, is to make sure that the output of the extractor, in this case, the extractor is g of x. Our goal is to argue that the output looks random to the attacker, right? And in this case, it will not look random to the attacker because the attacker knows x.
So that's my point, is that x is not a fixed big string. X is like a distribution, right? So if the adversary says, okay, let me query myself after I receive the challenge, let me query the random oracle, then the attacker will sample another random bit string, a fixed one, and then query the random oracle.
In each experiment, so yes, overall in the experiment, it's x is a distribution, but in any particular run of the experiment, x will be a particular string sample from the distribution. So what I'm saying is, in this particular game, the attacker can sample a truly uniform x, but of course, the attacker knows that yes, from the outside, that x looks truly uniform, but the attacker sampled it, so it knows it. So yeah, it will win the game, so that will not work. So one fix I suggested to condition on the state. That fix also doesn't work because, I already gave his answer, because here is another example over here. So what I'm saying is there is a harder attack which I'm not presenting. I had slides about it. Maybe I should have presented it. But let me tell you the right solution. The solution which is right.
Yeah, you answered my question along the way. Thanks.
Great. So let me tell you the solution which happens to be the right solution in the STO example. But yeah, I encourage you to look at the extractor fixing attacks that gave us a lot of trouble for this paper and for some other Eurocrypt paper. But this happens to be the right solution. The solution is to say, you know what? I want to condition on the list, not just on the state of the attacker. Yes, the attacker has to forget something. That's natural. But also the other restriction on the attacker we make that the attacker, that X should have entropy condition on the list of random oracles, random oracle queries that the attacker has made. So it looks a little bit strange. That's why I was like that. The other attack, which I'm not presenting, would have been useful to understand why this is the right solution. But intuitively, at least this G of 0 thing, if the attacker only makes one query, G of 0, then, for example, this condition wouldn't be true, right? There is only one query, so X doesn't have, any entropy condition on this. So sorry, G of 0, in this case, X will be G of 0. And G of 0 will not have any entropy condition on the input-output of the random oracle. Yeah.
So this condition that you're conditioning on the state and the random oracle queries looks a bit artificial in the sense that it's not efficiently measurable, right?
Yeah.
So
that's a good point.
do you want to say that we only quantify our adversaries from some class that satisfy this condition?
Yeah, that's a good question. You can view it as a weakness, even though we did manage to prove good results about it, but you're right. So in general, measuring entropy is hard. So for all our definitions, unfortunately, they have this feature that this is not an efficiently falsifiable assumption. So, you can view it as a positive or a negative. I'll present a positive view on your objection, but there is a negative view. So the positive view on this objection is entropy estimation is a hard problem. So in principle, if we want to talk about adversarial sources, the sources that produce of the attacker, it's infeasible. There are hardness results. It's infeasible for our security game to test if the attacker actually gave us entropy or not. Right? There is this reduction to statistical difference. I mean, there are all kinds of theoretical results for hidden Markov models. There are a lot of results that shows that in general, I cannot, if I wanted to say that I can actually test if the attacker didn't cheat, didn't give me something which doesn't have entropy, I cannot do it. So I have to basically rely on the attacker to be legitimate, which a condition I cannot check. So that's kind of a negative view. But a positive view is without solving, this definition is meaningful. Without solving an infeasible problem of entropy estimation, basically the design of our PRNGs will be of the following flavor. I said, without solving entropy estimation problem, I can say that as long as the attacker, so basically, yes, my PRNG cannot tell if it has enough entropy or not. But whenever it has enough entropy, it works. So I want to say how to extract from any distribution which has enough entropy, even though I cannot myself test if it has enough entropy. So I can have a definition which is meaningful mathematically, for which I can do proofs. But in reality, it will have this limitation that at the end of the day, if I run my computer and I'll do something like that, and at the end of the day, basically, I should decide, okay, should I use this RSA key or not? Is it safe or not? I cannot tell. I cannot mathematically estimate entropy. I can do heuristics, but basically say as long as I kind of believe that the world give me enough entropy in this 5 seconds that the computer booted up or something like that, as long as it gave me enough entropy, I didn't screw up in my extraction. And you will see there are plenty of examples, I'll give you some surprising example where the extraction would screw up despite having enough entropy. So I view it as a kind of positive feature, yeah.
Okay. So why don't you split the source or the adversary into a source and a distinguisher?
Sorry,
So splitting the adversary into a source and a distinguisher does not work?
Yeah, so in the previous definition, we actually explicitly split, I mean, it's a kind of equivalent, but yeah, we kind of say, I mean, I make the definition stronger. So it's true, I split it into the source and the distinguisher, except the source can pass the state, like this one-way information, it can pass the state sigma. So whether it's the same person or not, it's like a syntactic view. You can think of them as different people, but to make the definition stronger, I allow some partial information from the source so probably the better way to think about it logically, but mathematically it's the same, is yes, the source kind of produce both x and sigma is the partial information that it gives to the attacker, and x is the real thing that it gave to our RNG. So this is a way to think about it. But mathematically it's stronger, right? That the same guy kind of produced both things, but has amnesia and forgot something.
But I think then this is why you get the requirement to measure entropy, right?
Yeah. Yeah, so I mean, yeah, you definitely need to have some kind of state, but the additional thing to make sense of our problem, which turns out we tried many things to do it, it turned out this happens to be the most robust way, which happens to lead to the interesting results for us.
And in practice, how would you justify someone forgetting information?
So I'll try to give you, in the next bullet, I'll try to give you a justification. I mean, I have the whole backup slide, which I erased, but I'll try to say in words, but on the next slide, on the next bullet, I'll talk about your question, yeah.
Yeah, so moving a bit ahead, so can you instantiate this framework using universal computational extractors in the sense that the adversary gives some input to this, say, a hash function or something, and then you pass some states to the second?
So this is good. I mean, I have a backup slide, so we'll do better. So it turns out I don't need universal computational extractors. I will just use, so if you have a Eurocrypt paper follow-up, so if you're interested, actually, I have a backup slide. I'll put it, I'll uncomment it, and I'll show it. So for now, we'll do the random oracle thing. There is an interesting question. Is there a standard model formalization of this? And we had a paper at Eurocrypt 2020 for which I started to make slides, but I decided I have too much. But yeah, if you're interested, I'll give you a backup slide and I'll tell you what we achieved. The snapshot is, yes, we can make something meaningful, and I'm like super excited because I didn't think it was possible. And it was possible even without using UCE. It turns out UCE solved, I don't want to say a harder problem. Well, it solved a harder problem, except it didn't solve it, it just assumed it away. So we managed to solve a harder problem without assuming it away, but the constructions are impractical. I mean, they're like using like some DDH and some target lossy, whatever, some function. So we showed a theoretical way to do extraction in a setting which I didn't think was possible in the standard model. But unfortunately, in the same paper, we also had some negative results that whatever way, our theoretical definition, traditional cryptographic functions likely satisfied, but cannot be reduced to a standard assumption. So it was like some kind of positive. Yes, we believe that SHA will satisfy whatever the standard definition in our follow-up paper is, but I can never prove it based on something clean. Anyway, I mean, I'd be happy to talk about it. It's a fascinating topic. I decided to stay away from it, but if you have time, maybe I'll show you the backup slide about our, but yeah, great question.
Thanks.
Yeah, so excellent. So, okay, so those are excellent questions. Thank you guys for looking ahead. But for now, let's look at the more basic thing just to get some intuition for people who haven't seen it. So this will be our definition for now. That say basically the attacker has to, and this list is not just the inputs, it's input output. So for example, this G of 0 attack, the list will contain both 0 and the output G of 0. So condition of that, obviously X will not have, G of 0 will not have entropy. And in fact, so now this point about is it reasonable definition, so now we are entering the well of philosophy, but I believe it's a good compromise and it's reasonable. I have the whole slide about it here. I condense into basically this one sentence. So we believe it relatively naturally models nature. And the fact that the entropy comes externally, it's not, so in reality, this timing of interrupt, the fact that you cannot measure the last like nanoseconds of interrupt, it's not because, somehow, somewhere on the computer evaluated G of 0. So the timing of interrupt is not really, the hardness of estimating timing of interrupts is not really because G of 0. Yet G of 0 was evaluated, maybe affected when the timing really happened, but there is some internal, jitter in the clock that makes it hard to predict it. So somehow this seems to measure the fact that there is some external randomness. But yes, that randomness could depend on the random oracle interaction, but there is some randomness externally. And it's easy to see that this condition implies that X has entropy condition both on sigma and in the entire random oracle. Because L is the only information, it's like by chain rule in some sense. So yeah, we thought about it a lot and we really like this condition. I am a believer in this condition, but of course I am biased. So yeah, so it can depend on random oracle interaction, but has this internal. So this will be our notion of oracle-dependent sources, intuitively. At least for this simple example, as our definition is much more general because we look at other extractors, not just a monolithic random oracle, as we will see. But this is a flavor of our definition. Okay, so so now we can have the full definition. In fact, remember the trivial bound in the oracle independence sense? With this definition, we actually get exactly the same bound. So in some sense, what I'm saying is this is the right definition to get this result, but for significantly more sources. And in fact, the intuition, so it's the same as a random oracle independent bound, but for many more sources. For example, I'm allowing you to call G on anything, whatever, as long as you kind of has to produce some extra randomness to condition for this condition to hold. It now includes significantly more sources. And the proof intuition is, somewhat very similar because basically I want to say that after the attacker output X, this condition ensures that at the time it output X, even condition on the queries that the attacker made so far, X still has enough entropy. So after that, basically, you can still do the same thing. And whatever up to Q queries that it has, in each query, the probability that the queried random oracle is at most 2 to the minus gamma, and the same union bound holds. So in some sense, I feel like this is the right proof of this thing, and somehow it includes many more sources. So any question about this so far? But yeah, it's a good discussion. Yeah.
Maybe one short question. Would it make sense to then restrict the adversary here that he is not allowed to, for example, query X with the
yes,
values
as a standard model we did. There are variants which would be kind of almost equivalent, but we could, so in the standard model, indeed, we actually make a slightly stronger definition where, so this is implied that, because the list is short, so I mean, yeah, you can actually argue if you make like Q queries, if you use one of the points, the most entropy you can get is log Q. It's a simple compression argument. So maybe with there are variants. I don't think they will change things dramatically, but in the standard model variant, we actually did something like that. We actually had something slightly stronger. Yeah, it's probably possible. Yeah. So good point. Yeah, great. So this was kind of a warm-up. So one thing I want to say, so this was a computational version. So in particular here, G could have outputs like millions of bits. It's like one of those standard things that the length of the random oracle doesn't matter. We can also have an information theoretic version for the same definition. So here the attacker has these two stages. At the time at the sampling stage, the attacker has bounded number of queries to the random oracle. Otherwise, the impossibility results come back. It's easy to see. Output X, the condition has to satisfy it. Now the challenger has this thing, and now the attacker can, after that, it's kind of too late. We allow the attacker to read the entire random oracle. So this is models this thing which we call everlasting privacy. So just kind of models the fact that, yeah, nature probably is not going to depend on the entire random oracle, but it could depend a little bit. But after that, even if the entire random oracle is read, we want information theoretic security. So this model makes sense, and in this case, the proof is more complicated. In fact, it uses techniques from leftover hash lemma. You have to be like a little bit subtle hybrid argument. Not very hard, but you have to like do it in the right order. And basically, you get the same term here, which is intuitively that the attacker cannot query it here. But also now, basically, if k is a number of bits, sorry, I'm switching letters from m to k. So k, previously k was mean entropy, and gamma didn't exist. But now k is output length, and gamma is a mean entropy. But basically, it's the same thing. This is a term from leftover hash lemma. Over here, so and it kind of makes sense. I cannot extract more than the entropy I have, and now it's information theoretic in this sense. So good. So this is the information theoretic version, and yeah. So this kind of, you can think theoretically, you can view it as random oracle as a large seed. So anyway, so this is, I think, all very nice. So the first question is, okay, great. So should I move to the next topic? Are we done with extraction? And the answer is no, it's only a warm-up, but yeah, please ask questions. Because in reality, we don't have this monolithic, the sources could be long, and we don't have in reality a monolithic like random oracle, on variable length input. In reality, we have to build it, what we call an online extractor. Right? So in reality, the source may become slowly, like many interrupts, and you need to build something based on like fixed length primitive. So let me tell you what an online extractor is, and then we'll revisit our results from this kind of perspective. But yeah, if there are any questions, I'm happy to, yeah.
So the proof there, is it using some bit fixing technique, the Vonru and something like that, or it's pure leftover hash lemma?
Sorry, this one? Yeah, basically it's a combination. You have like two hybrids. In one hybrid, you do basically like carefully using the entropy to get this term that the attacker didn't query it. And once the attacker didn't query the random oracle, basically you have to redo the leftover hash lemma proof in this this kind of setting. But yeah, it's a little bit more complicated than the previous argument.
But you're not using that thing where you fix points inputs on the random oracle?
No, it's basically leftover hash lemma is just adapted to this setting. We just need to argue that the conditioning on this event. Yeah, I had, like, as I said, in the talk which was dedicated to this, I had like a little bit more details, but it's not very hard to see. Yeah, a little bit subtle, but yeah, there is nothing, no deep things about fixed points or anything like that comes up. It's just you have to be careful. But yeah, it's basically leftover hash lemma adapted to the setting.
Don't you need to break the independence between the to use the leftover hash lemma? You need to break the dependence between the source and the seed, right?
Yeah, so basically I have to define some particular event, and once I argue that the attacker didn't query random oracle, I can define kind of a residual random oracle, and I view it as a seed, and then things kind of work out. In the same, I use collision probability. So yeah, you have to be a little bit careful. The proof is longer than the proof in the non-everlasting security setting, but it's not nothing deep is happening there, at least not yet. The deep stuff will happen in the other things. That paper is like, I think, like maybe 80 pages and so on that I'm presenting. So this was like something warm up in the introduction or some section, and then the difficult part will come after we do this online extractor. Those things are unfortunately, significantly more complicated. But fortunately, I will just basically tell you the flavor of the results and not tell you the proof, just hint on the proof. But yeah, even the definitions. So there are small salties. The paper took a long time to write, but I was very happy about that paper because it took like many years where we tried to kind of formalize things properly. And anyway, I'll talk about it, but you will see the results. But yeah, that's so what I'm going to show you here in pictures, unfortunately, is much more complicated than the previous proofs. But so let's first kind of go to the easy, like Staples red button. So let's try to define what an online extractor is in this idealized model. So here we modeled explicitly the fact that X is not comes right away. But it comes slowly, like interrupt after interrupt, and you kind of you have to keep accumulating some state. So I have to introduce explicitly the state. Inside my RNG, there is a bounded state, like a bunch of registers or something like that. And every time, and now, there are basically, we are back to the syntax. Well, for now, I'm still looking at the online extractor. I'm not yet at the PRNG setting. It's still a one-time extraction, but the input is long, and it comes gradually. So technically, there are two procedures. The first procedure is the refresh procedure. This is like happens inside the computer. Before the user presses a button, every time there is a new interrupt, you have to update internally the state and apply this refresh procedure. Take the state and an input, and you refresh the state. And finally, when the user presses a button, there is this finalize procedure that takes the state and actually produces output. Right? So this is just the syntax of online extractor. And the security is the same. We just want, the security is the same as what I kind of wrote before. It's just the syntax is fine-grained, but the security is the same. We just want y to be indistinguishable from random. The experiment is just written here, so nothing deep. The only thing which is interesting, in our case, we'll look at the idealized model. So here we assume that both this procedure, refresh and finalize, can depend on some idealized primitive, some fixed length idealized primitive, like a compression function or random permutation or ideal cipher or something like that, depending on the construction. And so everything kind of is relative to it. And when we define the legitimate notion of entropy, we always condition on the queries. Right? This says attacker can produce the source, but now we condition the output. There is some online extractor construction, which will be more complicated, but we always condition on the queries that the attacker made to this little object. Right, to the list of queries that the attacker made to the little object. So any questions so far about the new syntax? And so hopefully we'll see some constructions and we will see what we are talking about. So in particular, let's look at an example. So here is a very popular extractor which is used all the time. So this is CBC Mac. So here I'm saying the object in question is a permutation, a fixed length permutation. We're going to model it as a, in this case you will see we don't need to model it anything, you will see why. We'll model it as a random permutation. And this is like you have a fixed state and input comes in, you just apply permutation plus another permutation and so on. So this is our refresh function. Right? The state is just whatever happens on the wire. And then when there is a new input x, you just XOR it, apply permutations, that's how you update the state. Right? And the finalized output is just the answer. Right? So in this case, this would be, we can do, actually, we don't really care what finalize is, as we'll see. I don't care what you do for finalize. You can hash something. As we'll see, it's not relevant in a second. Okay, so this is, I'm just telling you the CBC max. This is a refresh function of the CBC max. And it's a very popular construction. In fact, in my early paper in Crypto 2004, we looked at it in the random oracle independent setting, and we proved that this is a good extractor. In fact, we had this tighter bound. So this is, in the random oracle independent setting, it was a good design. Also, it's one of the suggestions in the standard. Remember, it always is this immature standard. So it's one of the suggested constructions in the standard to use the CBC math. And also Intel RNG, this is what Intel RNG uses. It has its physical sources of entropy. And the way it post-processes is using CBC math. So it seems like that should be a secure construction. Now we have our first test case. Can we prove it secure in the Oracle dependent setting? So we have a lot of kind of supporting evidence that it should be secure, right? Because, three kind of supporting evidences that a lot of smart people thought about it and should be secure. So anybody wants to bet some money on its security, I'll take it. So the answer actually surprisingly was no. So that's like the first time. So yeah, in the Oracle independent setting, this natural construction was secure. But in the Oracle dependent setting, at least according to our definition, which we like, and hopefully I justified it, it happens to be insecure. So let me show you the attack. So and hopefully with this attack, you will see a little bit some of the subtleties. So because it seems like a priori, you can say, oh, it's kind of trivial. Of course, you trivialized everything. But I'm saying, no, it's actually not completely trivial. You have to be careful. Some things are secure, some things are not secure. All right, so we're going to do attack. I'll pretend to be, well, actually, it's kind of funny. The only two things that I'm going to show you technically, I'm a proof guy, right? I do proofs. But the only things that just for the purposes of keeping the presentation light, I'm going to show you two attacks. So this is unusual. So let me show you the first attack, which is the attack on this CBC Mac. So first, let's remind the definition. So in this case, the attacker and the challenger has Oracle access to this random permutation. But for the attack, it doesn't matter. It's random. We'll break any permutation. We'll show it doesn't really matter what permutation you use. It's not going to be secure in our model. And the attacker makes a bunch of queries and outputs this long input x with the same security notion. It doesn't have to be output one block at a time. It just outputs the whole thing. And then the challenger either will give it CBC MAC on it or uniform. And we have this condition that, non-triviality condition. Okay, so this is our definition. So let's try to break it. So here is the attack. So here is a particular attacker. So the goal of the attacker is to produce a string which has a lot of entropy, slowly, but I'm going to produce a lot of entropy, one bit at a time. I'm going to produce entropy that I'm going to forget, so I'm going to be legitimate. And yet, there is no way to finalize. No matter what finalize function you use, right? I didn't even commit to the finalize function. There is no way to prove security. It will be insecure. So here is the attack. For the first block of my input, I'm just going to flip a coin and either give you 0 to the n or 1 to the n. And forget. So I flip a coin, I'll forget later. But you can imagine that the moment I output, I commit it to x1, I'm going to forget it. Okay, it's just so that there is entropy even to me. So I'm going to give it, so I apply this pi. So what do I know about the state? The state here, after I've forgotten this coin, I myself forgot, but I know it's either pi of 0 or pi of 1, right, with probability 50-50. So my next coin is going to be, with probability 50% is going to be 0 to the n, whereas probability 50% is going to be pi plus pi. And now you can see how I'm using the Oracle dependent setting, because in the Oracle independent setting, I wouldn't be able to actually compute this, right? That's not allowed. I have to commit to the whole source before knowing the permutation. Here, I'm actually choosing my source depending on the permutation, but I am injecting fresh entropy, right? So I'm choosing this as probability 1/2 and forgetting it. So I put it here. So what do I know here? Well, if this is pi of 0 plus pi of 1, if I XOR it here, you can see that there are only two outcomes. With probability 50%, so if it's 0 to the n, I get either pi of 0 or pi of 1. But even if it's this string, if I XOR is a pi of 0 or pi of 1, only one of them cancels out, I still get the same distribution. So irrespective of these things, the output here is with probability, so it's the same state here. So as a distribution, nothing really changed here as a distribution. So you apply it again. So now the state here with probability 50% is going to be pi square of 0, with probability 50% is pi square of 1. So you can see what I'm going to do. My second guy is going to be with probability 50% 0 to the n, with probability 50% here, and so on. Right? So if you look at it at the end, you can see I injected basically L bits of entropy. One at a time, I inject like entropy that I forget immediately which one I injected. But at the end, the output has only one bit of entropy. Right? And I don't care what finalized. You know that the outcome is going to be only one bit of entropy. It's probability 50% this, it's probability 50% there. But, and my state, if you wish, So the state that I output is, this pi of L of 0 plus pi of L of 1, because this state will allow me to, call random oracle over here and so on. But yet my entropy condition is non-trivial because there are L bits of entropy absorbed. All those bits for every one of those coins, I forget this coin. It's easy to see that, I literally forget it, so I really have L bits of entropy. And only one bit in the state. Okay, so this is the attack. Any questions about the attack? Just so that you can kind of start to appreciate a little bit the notion that it's not like everything is secure suddenly in this notion. You have to be careful. So any questions about the attack? All right, so, okay, so I don't know what I'm writing here. Oh, even condition anyway. So this is a legitimate attacker and good. So all right, so we had some insecure thing. Let's actually see a secure construction. So what would be a secure construction? And that's actually where most of the paper is. And the proofs, unfortunately, are kind of long. So I'll just kind of tell you what we managed to prove secure. And hopefully, people find it useful. Like Linux is going to use some of those things and so on. So it's good. So one construction, now we look at other things. And we are, again, looking at practical things that are used in the real world. So the next thing that is used in the real world would be Merkle-Damgard, right? This is basically, I'll talk about Shai in a second. Based on a fixed length compression function. So the refresh function is just basically apply a compression function, right? That's like a canonical thing. And in this case, because we are talking about extraction, I'm not yet at the full general problem of PRNGs. It's just a one-time extraction. You can just output the final state S. Okay? So we proved again in the Oracle independent setting that was secure. But as you know from the CBC MAC example, it doesn't prove security here. But fortunately, this is secure. But yeah, it was like a pretty complicated proof. But happens to be secure, no surprises here. Yeah. So question? Or?
Yeah. Did you look at the sponge?
Sorry?
Did you look at the sponge?
I'll show sponge. Yeah, I'll give you. We have a lot of constructions. So I'll give you a summary of all. So one construction which is secure is this, which is good. So that's another positive result. We can also do an information. For the construction, we also give you both computational version and information theoretic. For information theoretic, outputting the whole state, it's easy to see it has no chance to be secure. It's just the output is too long. Irrespective of the entropy, just somehow, yeah, it's not very hard to see that, yeah, it's too much to output. But if you truncate it a little bit, and you can see exactly how much, it's if you truncate it a little bit, that will be secure. So information theoretically, right? Computationally, even the whole thing is secure. But if you want information theoretically, condition on the entire thing, you just need to truncate it, so which is good. So that will be a secure construction. So next, after we did this paper, I talked to Hugo Kravchik, and he was like, "What about HMAC?" So he forced us to do another like 10-page proof, but or whatever. So yeah, so for HMAC, we had to unfortunately redo the proof, but HMAC is something kind of annoying that the finalization function is more complicated. It has this iPad and OPAD or whatever something. But basically, the same proof worked, but we couldn't do it black box. We have to just cut and paste and with some minor changes. But yeah, anyway, HMAC is also secure, so that's good, right? Because it's used in the real world more frequently than, you know, people don't just extract compression function from SHA. They actually just use HMAC. So, but the good news, HMAC is secure. Also, one level below, if you want to say, oh, but in reality, the compression function of SHA is done using Davis-Myers construction with some ideal cipher. Well, again, we had to do a full 10-page proof, but like not that many new ideas were there, just a few more kind of cases. But fortunately, it happens to be secure. So abstractly, it kind of captures the fact that if you use SHA-2, it gives you good evidence that if you use SHA-2, it's secure, right? It will be likely to be secure. And the fact that you do the strengthening, it doesn't change anything. It's always in the model, so this is fine. Sponge, right? So next practical construction would be sponge. That's what something we can do. So for those of you to remind what the sponge is, it's basically a more conservative version of CBC. CBC mode didn't have this, I forgot how it's called, absorb, I don't know, whatever, one of those things. It only had the XOR part, and it was too aggressive in this way. But yeah, if you have some non-trivial part over here which you don't let the attacker XOR it, it turns out the construction is secure. So this is the refresh function. Here there is one subtlety. You cannot just output the whole thing at the end. You have to output only part of it. And indeed, the suggestion for the sponge, they actually have a suggestion how to use it as an extractor or something like that. It's only to output the top part. So if you output the top part, we prove that this is secure in our Oracle dependent setting. Right, so good. And actually, in this case, and this also with a different proof, it happens to also be secure even in the information theoretic setting with a more complicated proof, but it works out, with slightly weaker bound, but it works out. So this is great. And as I said, seed invariant was proven secure in some paper of Stefano, but this is the Oracle dependent setting. Okay, so the question, I guess, now is what about applications to seedless PRNGs? And fortunately, the answer is yes. In fact, in our paper, the first half of the paper was about extraction because that was like the heart of the problem. And some people just want extraction, right? Like online extractor is an interesting problem in itself. But now finally, so this is a seedless watermelon. Luckily, everything worked out. But I have to, in order to tell you that it all worked out, I actually have to define what it means to go from a line extractor to a PRNG with input. Okay, so finally, we are back to the PRNG. So finally, at least in this setting, I'm going to define the PRNG with input thing and how to adapt our construction. So the main difference from PRNG with input, instead of one output, right? So this is finalized and there is only one output. I can produce many outputs, right? So things could go and you can press button many times. Every time I press a button, there is an output. So technically, the only change is instead of just one-time finalized procedure that takes a state and produces output, the procedure now is called next, and this procedure not only produces output, but also tells you how to refresh the state. So now so this is the syntax of PRNG with input. There is a refresh procedure that takes state and X and produce new state, and kind of a reverse procedure next that takes the state and produces a new state in the output. And the attacker can in our adversarial setting, I'm not going to give you the full security game, even though towards the end I'll give you, when I prove some impossibility result, I'll give you a toy version of the security game. But basically, the attacker can make calls in any order, say, hey, entropic input, output, and another entropic input, whatever you want, and somehow, as long as the attacker is non-trivial, every time the attacker has to challenge, it has to have enough entropy. As long as we do that, we'll have a definition of security. And of course, the key point is a new capability that we want to give to the attacker is state compromise. That's the whole point. So that if at any point you compromise a state, you should be able to recover it as long as you give me enough fresh entropy, you should be able to recover. So the attacker has a lot of power here to produce things, to forget things, to compromise state, and so on.
The Merkle-Damgard construction, it has to be chopped Merkle-Damgard, right?
Yes, I'll show you how to adapt that's actually the next thing. I'm going to show you how to adapt the extractor things to PRNGs with input.
So is it a coincidence that both constructions turn out to be indifferentiable? So is your game a special case of indifferentiability game?
Not that I know. Yes, there could be some connection to indifferentiability, but as far as I know, our notion of entropy and this legitimate attackers, I don't have any formal connection to indifferentiability. I mean, we really had to give a definition of online extractor separately, PRNG with input separately. As far as I know, I don't know any formal relation to indifferentiability. That if, I mean, it's a good question, but yeah, with a simulator, it's like, yeah, I don't know. We just define it separately and just concentrated on randomness extraction here. Yeah, I'm sure there I mean, we can talk offline, I'll think, but I mean, we thought about it and there are all kinds of issues, but I'll have time to, I will need some time to remember the issues. I don't think it will work, but yeah. Okay, so back to this kind of things. With some tweaks, all will give us the full PRNGs with input. You just need to be careful. So, I mean, you asked about Merkle-Damgard. The tweaks are simple. I'll give you the tweaks, the most non-trivial tweaks for the sponge, right? So, but we do tweaks for all of them, how to analyze all of them with PRNG with input. So for the sponge, the refresh procedure is the same, but now instead of analyze, I need to tell you the next procedure. So remember, the output was just S sub r. And this actually is a function proposed in a different paper for different reasons. That was a function proposed for Hutchinson for efficiency reasons. But it turns out this was actually very helpful in our setting as well. For maybe related reasons, but anyway, so we are going to use it. So this is going to be the next procedure. So as before, I'm going to output the top part, just like in the extractor part, that's good. But now I need to tell you how to refresh the state. The naive thing would be just to output the state by itself here, or possibly maybe pass it through a random permutation, but that doesn't help because the permutation is invertible. So there, if the attacker compromises the output of RNG here, even if I have a random permutation here, I can just go back and trivially break the previous output, right? Because I want, forward security is also part of the thing, that if I compromise the state now, I shouldn't be able to distinguish previous outputs, right? So if you don't do anything, it's not secure. So even if you just apply pi here, it's not going to be secure. But it turns out the simple fix that works, and hopefully is not that hard to implement, would be to do this kind of Davis-Myers fast-forward kind of XOR. Over here, if you do fast-forward XOR, now you cannot go back. So anyway, so this is a construction that works in our setting. Yeah, so and then this is a new state, and you can keep going. So as I said, I'm skipping the proofs, but hopefully, what we like also, these are practically motivated constructions. Yes, the proofs are complicated, but you give them one time, and you can, kind of keep going. And so hopefully practitioners and in a pretty general setting can use this constructions with confidence that as long as there is enough entropy, these cryptographic hash functions really work as randomness extractors, and even RNGs with inputs. Any questions before? Well, I'm going to ask a question. Are we done with PRNGs? And you see I have still some time, so I guess the answer is no. But any questions to the previous part, because we're going to switch gears and talk about something else.
This last modification was needed to make it a PRNG, you mean? Before you got on without that modification, it was an extractor, right?
Yeah. Well, so for the extractor, I don't need to tell you, because after finalize calls, the game is over, so I don't even need to design this. The finalize just outputs y. But if I'm saying if I need to keep going, then I cannot just, this construction wouldn't be secure. If I need to keep going, this is not secure because I can compromise my state over here. And then because pi is invertible, I can just go back and look at the top part and produce the previous output. And that's not forward secure. So I need to make some change. This is the simplest change that works. And coincidentally was suggested for a different reason by Hutchinson in the Oracle independent setting. So good. So actually, I think we're doing well for time, but yeah, so are we done with RNG? So it turns out no, so there is another issue which I didn't know, but when I was working with Apple people, somehow they kind of showed me some piece of the code and I couldn't understand where it comes from. And then, it turned out that they introduced a whole kind of new animal of problems for us, which is this issue of no time to hash. So yeah, so this is a movie that I just watched. Actually, coincidence, on the airplane here, I was too tired to work. I decided to watch a James Bond movie, the latest one, No Time to Die, good movie, so I recommend it. So, but we used it, so my co-authors are more cool than me, so they watched it like even last year or knew about its production. So that's how the paper is called No Time to Hash, something. So, so what is the problem? The problem is that for real PRNGs, yeah, I give you this kind of cool designs, you know, like sponge and whatever, but this interrupts, there could be like millions or thousands of them every like second. It's just as fast as, you know, sponge or whatever other construction size, just you don't have enough time to just evaluate, you know, the hash function for every interrupt. So in fact, talking also to this Jason guy from Linux, he also by Niels Ferguson and McGrath says, I have like, I don't know, like 7, you know, clock cycles to implement the refresh procedure on every interrupt. It's like, or something like that. I don't know. I think 7 or maybe 17 is the right number. I remember there was 7 involved somewhere. But so what do we do? So heuristic solution, which are used in every popular OS, even in Linux in a different form. So they use something very heuristic. So this is so implicitly, informally, I mean, they never define it in refresh and next, but informally, they split the refresh procedure into 2 parts, the fast part and the slow part. So the fast part happens on every interrupt. So this is like a fast animal, cheetah or something like that. So you do something very fast, you know, probably heuristic. I mean, we'll see the constructions that people use in the real world. And then, you know, more slowly, when there is enough time, kind of you're going to use, you know, cryptographic hash functions. Every, like, I don't know, Apple and Microsoft do it differently. Apple does it based on time. Microsoft does it based on the number of interrupts. But after a while, you will like take your state and apply cryptographic hash functions. Then again, you do cheetah, and then after a while, you use, you know, the turtle, okay? So, and I even will give it different letters. So X is going to be, I'm going to denote the time, the X is going to be the input. R instead of the output of the extractor, again, I'm changing letters. It's called register usually. So this is something super fast. It's done like register. So this is like the super fast entropy accumulation happens in register. We'll call the output RAR. And when the turtle is called, this is what back to our state S. That's like our slow state S. And when Alice calls this thing, Alice interacts not with cheetah. Alice interacts with this turtle stuff. That's where like hash functions are used and so on. But basically, so we have this X. Every time it gets updates this R. In fact, there are many R's. And then a bunch of those R's will be passed to the state. Anyway, so hopefully the picture makes sense. Any questions? This is a pragmatic thing. And what the previous part did, it kind of showed you some good evidence that appropriately designed cryptographic hash functions are a good representation of the turtle. So what about the cheetah? What people do for the cheetah thing, right? So, so I'm going to show it on the next slide. But basically, if you look at the, for example, Windows 10, so that was like after Bug and Niels Ferguson finally he wrote up this kind of thing, so we could cite it in our paper. I mean, I knew it from private discussion with him, but finally he made it public, so we could write a paper at Crypto last year, citing like official sources. So this is what kind of happens in this fast entropy accumulation. So I'll actually tell you the construction, but here I want to make a slightly different point. So you have these interrupts, and potentially these interrupts, they might have very little entropy. Some of them might not have any entropy at all. And then you do something super fast and heuristic, and hopefully you accumulate non-trivial amount of entropy here. You know, so at least you don't lose entropy, but hopefully you kind of accumulate entropy. Yeah, because here some of those things could be, like there could be a very unfortunate situation. You have a lot of entropy, and some who use crop, and all this entropy is like wasted. Forget about not accumulated, you can actually lose entropy. You have like some entropy, and then no entropy just kind of loses entropy. So that would be a disaster. But then more slowly the turtle comes, and it finally, hopefully the turtle is good. We have this super strong results that I showed you here, and it gives you something which is kind of, I don't know. So black means in this case entropy. It's random, and white means non-random, right? So you have very little randomness, you get a little bit more, and then here eventually you'll get everything random. Yeah.
Why is it on? Yeah, why is the fast entropy accumulation, why does it get many inputs? I was under the impression that you call it once for every
interrupt. It gets one by one, yeah. It gets, I mean, I'm just showing you the result of iterated. Yeah, it gets like, for every interrupt it gets, so you're right. I mean, you will see, I'm going to zoom in. That's actually, okay, so there is like a zoom in thing. So I'm going to zoom in here. You will see exactly what is happening. Here I'm just saying conceptually 1 by 1, yeah. This happens like 1 by 1. There is like a lot of like these little interrupts 1 by 1. Here the same, 1 by 1, there are a lot of those registers. So this is kind of a schematic thing of what happens eventually, but we're going to zoom in. The point I was trying to make here, for the problem of super fast entropy accumulation, right? So looking ahead, we will have the following dilemma. I have to do something super fast. I cannot afford cryptographic hash functions. Obviously, I wouldn't be able to get super good provable result on something which is like has 7 clock cycles and so on. Right, it just will be like something like super heuristic. But at least something good going on for me. I don't really need this to be uniform. I don't need to solve the extraction as long as I don't lose entropy even. But as long as I accumulate a little bit of entropy, it's good enough for me. So basically, my point is that the super fast part, I just need condensing, or I need entropy accumulation. I don't need extraction. Extraction is an overkill. Extraction will be solved by what I talked to you before, right? Extraction is solved by what I talked before. I just need basically accumulation. In fact, just not losing entropy is good enough for these kind of things, okay? And the other thing, so now let's zoom in and back to your question, how does it really look, right? Okay, so what is a cheetah? So this is actually the entropy accumulator for both Windows and Apple. Linux used something else, but now they're going to switch to something even else, but it's not yet finalized, so we don't know yet what Linux is going to do. I'm in talks with Jason about it, but the things which I actually done is a very simple construction. It's rotating XOR. You take the registers, there are many of them, like 32 of them. Yeah, so this is actually, sorry, the answer to your question actually, yeah, I mean, in reality what happens is, yes, this picture meant to represent that there are 32 little registers. And yeah, so anyway, this picture is overly simplistic. But basically, in reality, there are several of those registers, and every time one of those, an interrupt comes and it affects one of those registers in a round-robin fashion. But we can ignore this particular thing, and the construction is super simple. So in fact, they use rotation by 5 and XOR. So alpha is the rotation amount. So on 32-bit architectures, they use rotation by 5. On 64-bit architectures, they use rotation by 19. Very particular numbers, as you can see. And the construction is very simple. So you have one of those registers arise. There are 32 of them. That was like what's meant to be on the previous slide. It has maybe a little bit of entropy. You don't know how much it has. It has a new interrupt. Also, the timing is a 32-bit, I don't know, integer or something. And what it does, it like rotates this thing by 5. So maybe the entropy moves around here. Then XOR. So in this super simplistic example, it doesn't have to be like that. Hopefully, you get a little bit more entropy. You get the entropy a little bit from the tail. So hopefully, you get a little bit more entropy. Right, so this is kind of what is done. Super simple, very fast, like just several clock cycles, rotate and XOR. Right, so this is what people do in practice for super fast entropy accumulation. And of course, we can ask questions, well, why rotation? So we have some answers, so I'll answer your question in a second. So definitely, well, one answer why is like I need something super fast. What is faster than rotation and XOR? So this is one answer, but of course, we want to ask this why for security. Why rotation really works? Maybe I should use like cyclic, maybe I should use some other shift, or maybe I use, I don't know, some NAND, or I don't know, something like that. Also, why 5? Where are those numbers 5, 19? So basically, the point is, can we prove anything? Yeah.
The question is just like in the picture, you sort of assume that the entropy is sort of consecutive in a sense.
Yeah, of course, in the analysis, we will not assume any of that. It's just for illustration. Yeah, of course. Yeah,
it was related then to rotation, right? Because if it were somehow scattered along the string.
Yeah, they will be scattered around in a totally crazy way. We'll have, yeah. It's like, I don't know. It's just like for illustration.
Okay.
Yeah. Obviously, we don't know. Yeah. 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 Good point. Sorry? Yeah, so as you'll see, yeah, it will be easy to see that it has to be something relatively prime to 32, but even relatively prime is not enough. Yeah, so like a lot of numbers are bad. So as we'll see, I'm going to kind of jump ahead. I will tell you the whole theory how to analyze those things. And in particular, we'll see why 5 is better than 1 or, I don't know, like 13 or something, So we'll see, some, like for example, 5 will be better than 11, much better than 11, and you will see, hopefully you will see why, but we'll see. Right, so we will try to find, so in this crypto paper last year and also ITC paper that looks at some kind of related problem, we try to find a mathematical or cryptographic justification for this super fast entropy accumulation. And basically, yes, so just kind of to summarize, this heuristic solution is to separate slow refresh and fast refresh, but our challenge is we have to cut corners. So in the random oracle results or whatever ideal cipher results before, we try to defeat super powerful attackers, like unrealistic attackers, define a very general motion of entropy, arbitrary, basically unbounded attackers just bound the number of random oracle queries. So super, powerful results. Here we will have to come corners. I mean, obviously, it's very easy to defeat this rotating SOR, but so we'll have to have some kind of heuristic, but hopefully a valuable heuristic. So this is our challenge. We need to come to cut corners to prove anything, but hopefully cut corners in a way which is consistent with how people design those things, and we'll explain from a theoretical perspective some of those effects. And this is like, remember I told you back to the whole structure, I said there are these 4 high-level ways to overcome impossibilities. That was like the coolest maybe theoretically with like, we try to save every bit and so on, but somehow in practice people don't use it because it's catastrophic. This is great, but it doesn't help with super fast entropy accumulation. The last 2 restrictions, which have a lot of history, where you limit the class of horses and weaken security, we're actually going to use here kind of those simultaneously. One assumption that we are going to make, unrealistically, but just to explain, because I said we have to cut corners, and hopefully you will see that what we did is better than nothing. For in our analysis, we'll assume the timing of interrupts that every xi is independent from the previous one. In reality, it's not true, but hopefully it's enough of a heuristic to, you will see we'll get meaningful results. So hopefully it explains something. So we'll have, that's one of the corners that we'll have to cut. And the other thing, as I said on the previous slide, I don't need extraction, like condensing is good enough because extraction will be handled by a different layer, like a random oracle and so on, okay? And the technique, not maybe as advanced as in the Theis paper, but also somehow surprisingly, that's why I laughed. I mean, this is like a particular, it's like really stuff that is used in the real world, like Apple, whatever, all those guys use specific things, like super practical applied people design those numbers with intuition, but in the proof we'll actually use some tools from Fourier analysis, like, Parseval identity and convolutions, and, anyway, it was, some kind of cute things, which I would say like somewhat mathematical. I don't know if they're combinatorial. I'll call them even combinatorial so that it's consistent with the topic of the school. But yeah, it was kind of cool that we looked at them, super applied thing, but used techniques from theory to hopefully explain things. All right, so let me give you a little bit of a summary of the 2 papers that we published on the subject. And I think actually, maybe we'll finish earlier, but I can also always switch to the board and answer questions and things like that. So yeah, I wasn't going to go into details, but let me tell you the summary of, there are like 2 complementary papers, one at Crypto and one at IATC, where we looked at this question, but from 2 slightly kind of complementary points. So in the Crypto paper, we looked at a more restricted set of permutation because we wanted like very concrete results, like concrete efficiency so that you can see that 5 is better than 11 and things like that. We looked at only permutations, so A. So in general, you can imagine A is like any invertible matrix. Yeah, if it's not invertible, somehow it's clear that we want like an invertible matrix. Like rotation, cyclic rotation is an invertible matrix, but it's also a permutation matrix, just like flips bits, right? So in this paper, we looked at the transformations that only like flip bits, because also intuitively maybe faster than general linear transformations. In this paper, I allowed you arbitrary linear transformation. And linear was kind of an abstraction for efficient enough in practice, but of course, maybe not at the operating system level. I cannot like have a dense matrix, but So in ITC paper, we allowed any linear transformation, here only permutation matrices. And of course, the way we split the paper, we worked on everything. We got a bunch of results, and then it was like made a decision how to split up the results. So here we look at the concrete condensing efficiency. We got like really concrete bounds. I'm going to show you plots and things like that. That we obtained through our Fourier analysis thing. In this paper, we concentrated on this kind of asymptotic, kind of results, more qualitative results. I'll tell you what the results are in a second. So here, at ITC paper, we look at this general question that each, we allow xi, so this is like this kind of complementary thing. So, xi could be arbitrary mean entropy k distribution, that's good. But the bad thing, basically the attacker can choose arbitrary mean entropy k distribution, but once the attacker chooses the distribution, all the sample x1, x2, x3, and so on has to come from the same, so essentially it's IID, independent, identically distributed. Right? And it's easy to see, maybe I'll show it on the board. Without this assumption, there is no hope to prove anything, and like trivially, I'll justify, so maybe I'll go to the board in a second after I present the result and show you that these restrictions are necessary, otherwise we cannot prove anything. There are easy counterexamples. So in ITC paper, we managed to look at general linear transformation. We allow arbitrary mean entropy k, but it has to be IID. So in the crypto paper, IID is like maybe too strict over this thing, so we wanted to find some kind of compromise. So we tried to model what it means for the timing of interrupts. What do we know about timing of interrupts? And intuitively, timing of interrupts is an example of what is called a two-monotone distributions. I don't know if you can see here. So this is like a two-monotone distribution. So, but basically, in timing of interrupts, intuitively, if you look at this timing, this 32-bit string, intuitively, nanoseconds are more unpredictable than milliseconds, are more unpredictable than seconds, and somehow years are always the same. Like the first few bits are kind of basically changed, very, very infrequently. So intuitively, these distributions have the properties that in this particular case, the bits closer to one side are more unpredictable than the bits, on the other side. And it turns out, so we actually did something much more general than this. We defined this class of two monotone distributions. And basically, it's written here, so it means that if you look at this n-bit number and view it as an integer, as opposed to an n-bit string, view it as a number from 1 to 2 to the n, right? We can now define, thinking of them as an integer, we can imagine probability density functions that goes from 1 to 2 to the n. And two monotone distribution is any distribution where there is at most one peak. Right, so it models like Laplacian distribution, Gaussian distribution, and so on. For timing of interrupt, intuitively, this center is when the interval really happened in the ideal world, and this is like the further away from the real time that the interval happens, the more, less likely you kind of to observe it intuitively. So the two monotone distribution, essentially, we define it. So that's the distribution which has at most one peak if you view it as an integer. So we don't have the peak to be necessarily, but anyway, so this is how we define two monotone distributions. And unfortunately for Linux, it's not the case because Linux doesn't use only timing of interrupts. It uses some other crap, which is not two monotone. So we're still working with Jason to see if we can reconcile some of the results, but it looks kind of hard. So, but at least for Apple and Windows, to us, it seems like as a good compromise. But we don't need to be IID. So basically, we restricted the family of timing of interrupts. Basically, the attacker can choose at every point arbitrary two monotone distribution. And the entropy, it's up to the attacker. Some of them will have entropy 0 and so on. As long as, the condition will be the same as before. As long as overall there is enough entropy, I'm good. But I don't need to assume. But basically, we have to, well, okay, so there will be some gap. But basically, the important thing is, in this modeling, we restrict to the family of distribution, but they don't need to be identical. They're just independent, and at every time, the attacker can choose a different distribution, a different two monotone distribution. And here, unfortunately, it has to be IID. Because, it's very easy to, maybe I'll show you in the next 2 minutes, I'll show you counterexamples for both of those settings if we don't make those assumptions. Okay, so here are our results, okay, for two papers. So the result in crypto paper, at least qualitatively, if you don't care about the spins of condensing, anything, as you said, anything relatively prime to n actually works. So any rotation amount relatively prime to n works. And it's easy to see if something is not relatively prime, in principle, it has no hope to work. For example, if the number is 32 and we do rotation by 4, it's easy to have basically, let me see what would be the examples. You cannot have any entropy accumulation. Let's see, I'm blanking for now. 1 second, it's a simple example. If the distribution is, for example, let's say all the entropy comes in bits like 1, 5, 7, 11, and so on. So those bits always stays at 1, 5, 7, 11 because it's not relatively prime, so you have no hope to kind of accumulate more than this. So it's like relatively prime, as somebody pointed out, is necessary condition. We kind of show if you don't care about the rate of condensing, this is actually sufficient. This, any alpha kind of works, but the rate could be slow. On the other hand, for ITC paper, it doesn't really matter. At this level of generality, because linear transformation is invertible and it works for any entropy k distribution, is just kind of renaming the distribution, so it doesn't really matter. All alpha is kind of the same. But unfortunately, it only works for prime n. So yeah, so rotation works, but only for prime n and not all prime n, and prime n with some special condition. So, which is satisfied by some numbers, but not other numbers. But definitely 3264 will never satisfy this condition. So, but for some numbers, as I said, this paper is more theoretical. It's not. It's a little bit divorced with practice. But basically, what we showed is for special n, rotation would work. So all rotations are always the same. They either work or not. But when they work, it turns out, for special prime n. More specifically, if you want to know, it's like for prime n, where 2 is generator of Zn star. So it's like for prime n, where if you look at Zn star, 2 is actually generating the whole group. And there is, if you look at the proof, you will see exactly why. But here I'm just going to skip this part. So here the result was just kind of cool. So we basically have a characterization of extraction. For condensing, we don't have a characterization. It's kind of a messy. It's somewhat messy, but. In this model, extraction works if and only if A doesn't have any invariant subspaces. So if you think about like rotation, for example, rotation has some, at least 2 invariant subspaces, no matter what, right? So that's why rotation, okay, and when I say, here when I say they work as condensers, not necessarily extractors. But yeah, if you want to have an extractor in this kind of setting, if you want to really make sure that eventually you convert to fully uniform, rotation never works in this case, in particular because rotation has at least 2 invariant subspaces. A uniform distribution of all 0 strings and all 1 strings. Right? All 0 string, no matter how much rotated, it's all 0. All 1 string, no matter how much you rotate it, it's all 1. So even if you rotate XOR, if you have uniform distribution of all 0 all 1s, rotate XOR just keeps it all 0 all 1s, like the CBC example. And the same thing, rotation also preserves parity. So, for example, if another subspace which is invariant is all even parity strings. And again, you can see if my distribution uniform over all even parity string, if I state it like that, you never get an odd parity string by this transformation. Right? If you rotate an even parity string, it's still even parity. You XOR something even parity, you always stays at even parity. So that's why, for condensing, it would work for this special prime n, but for condensing up to n-1 bits of entropy. But if you want extraction, we have a full characterization, basically any matrix which doesn't have an invariant subspace. So if you have, some subspace and you apply this transformation, you have to kind of get out of this subspace. So, and in particular, an example of this transformation is field multiplication. So if you look at the field G of 2 to the n and you multiply by kind of a generator, it requires, actually maybe we have time, we'll see if we have time, I'm not sure yet, but I can show you the, the proof of this. That will be one thing that is not on the slides, but I show. But in particular, field multiplication, if you think about like reducible polynomials, it can be very fast. So you can implement field multiplication by, right, so if you think about, it's like you have a field element, you view it as a polynomial, and then you multiply by x. So multiplying by x is basically shifting by 1. It's like this rotation, but now you have to reduce it by the reducible polynomial, so it kind of corresponds to cyclic rotation and XOR. Right, so it's not very hard to see. So this could be like very, very fast. Of course, I'm not saying in practice people don't use field multiplication, but this is one of the suggestions that we conceivably could be considered. So it's conceivably could be considered, at least from this justification, that because field multiplication doesn't have any invariant subspaces, you can, but of course, IAD stuff is a little bit of a killer for these things. But anyways, so this is the examples. Right, so this is what we show in the ITC paper. So in the ITC paper, we show that this is an extractor if and only if A has no invariant subspaces, which is basically equivalent. You can actually, another theorem which we kind of prove is basically equivalent to some field multiplication. So this is the only transformation that always extracts, but rotation at least condenses, but only for special things. Okay, now let's look at this crypto paper, which is much more practically oriented. So here is what we did for the crypto paper. We defined this notion called covering number, which is a simple property of permutations, which what we show is governs the condensing speed. So, and I'm actually going to show it, I think, on the next slide, what the covering number is. And this, and it turns out the rotation for different alphas have very different covering numbers. And this kind of explains why some numbers are better than some other numbers. In particular, what we did, we really computed this covering number. We proved the theorem that covering number kind of governs the speed of condensing. And we show that actually Microsoft and Apple choices of this 519, Apple uses 7 or something like that. So it's actually pretty good, right? So numerically, we just computed these numbers. We looked at the plots. I'll show you the plots in a second. We show that they are quite good. But then we ask the question, can we actually prove it, right? Can we prove that, whatever the definition of covering number, can we prove that rotation always have good covering number? And that looks like requires some deep techniques from analytic number theory, which we don't know, even though we have some ideas how to prove it for special ends, like Fibonacci numbers or something like that. But for small numbers, a good thing, we can just plot it and we can see how it works, so that's good. So for practical things, we have a result. But as theoreticians, we could ask the question, can we define a permutation matrix which has a provably good covering number? And it turns out, yes, there is basically one canonical permutation matrix which has the best covering number. And in fact, the covering number is optimal. It's called bit reversed, we call it bit reversed rotation. I'll show you the picture of it. Unfortunately, when we talk to both Apple, Linux, and Microsoft, we don't know how to implement it in 7 cycles, even though it's a permutation matrix. We don't, so as I said, no chance. We're not going to use it. It's just, it will be too slow. People will kill us. But as a theoretical result, it's kind of cool that we discovered something which is both provably secure and, well, unfortunately not fast enough. But anyway, so this is the result. So what I'm going to show you maybe is the pictures for this. And if we have time or whatever time you give me at the end, we can go with dive inside one of those kind of topics if you want. So any questions before I show you the results? So I'm going to show you the results over here. I'm going to basically tell you a little bit what the covering number is and show you some pretty pictures. But yeah, I'm going to skip all the Fourier analytic proofs and all those things, but that was where the meat of the papers were. All right. So so this is, okay, so first let me tell you what the covering number is. I should have put it on the slide, I forgot. Yeah, I cut too much from the presentation. So the covering number is actually very simple. Yes, so the covering number is this number C of nk. So it depends both on the n will be like 32, it's the length of the input, and k is a parameter. So k can be anything from 1 to 32. And intuitively, the point is, so if you cover the first k bits black, the bits from 1 to k, this is n, so you draw them as, so this kind of intuitively, think about it, I have a uniform distribution which is uniform over k least significant bits. But the notion is fully combinatorial. It's just, and the question is, how many times right, remember it's a permutation matrix. So every time, I'll apply it to rotation, but every time, right, so I can apply this thing, and in case of rotation, after one rotation, it will move here. Maybe after the second rotation, I'm running out of colors, but it will move, well, in this case, it will move maybe here. The same. And so on. So the question, but basically the covering number means what is the smallest number of rotations that after I apply it, I cover the whole thing. Okay? So for example, just like some simple thing, if k is equal to 1, Cn1 is, sorry, not Cn1. So Cnk, if the, so this is a function of so this is a covering number of a permutation. So for example, it's like a simple observation that Cnk of rotation by 1 is n minus k plus 1. Because every time I rotate by 1, yeah, I have all these things, but I just cover only one more bit. And that kind of shows why rotation by 1 is a bad thing, and nobody will use rotation by 1, because if the entropy in least significant bits, it will tell a lot of like this little rotation by 1 until it starts to influences high order bits. So I want kind of a more aggressive rotation, right? I want like more aggressive rotation, but yeah. So, and of course, another kind of observation that C of nk of rotation by kn is optimal. So it's easy to see that I need at least, right, because intuitively I have only k bits of entropy in the input, so I need at least n over k. The covering number of anything has to be at least n over k. So if I'm lucky, if my rotation is, it's rotation by k, and the parameter k is the same, then I will get the optimal number for a particular k. The problem is I want I don't know what k is in reality. Like, so this permutation I designed myself, but this value k intuitively corresponds to the entropy of the input. Whereas, how many bits of entropy, sometimes the interrupts have a lot of entropy, sometimes they have a lot. So somehow I want one, I want to fix one rotation, let's say rotation by 5, and somehow this rotation of 5 has to simultaneously work for all values of k. Right? This is kind of my philosophy. I want to choose one thing because the operating system has to do the same thing. But no matter, whether I have a lot of entropy in my least significant bit, so a little bit of entropy, somehow the results have to be good. So anyway, so this is the definition of a covariant, but you see it's just purely combinatorial, right? So this, nobody can say this is not combinatorics, right? This is as combinatorial as it gets. So I don't know about the rest of the talks, but this is combinatorial. So this is a picture. So we can kind of compare different alphas. So the black line is n over k, is just the optimal, the low bound. We need to have at least n over k things to cover everything. And then we actually compute this covering number for different rotations, and you can see, so this plot here is the entropy amount, basically the value of k. So here we choose alpha equals 5, the rotation is by 5, and here we do the plot, and you can see somehow it's pretty good. It's close to the lower bound, which is kind of pretty good. For n equals 7, this is Apple's choice, actually. But Apple's choice arguably is a little bit better. It doesn't have such quite a big gap over here, at least from this kind of formalization. And then there are other choices. These are kind of the best choices that we found, with various things. So all of them are basically good, but something like 11, I didn't draw it, would be horrible. Why? Because 11 times 3 is 33, so somehow you would, intuitively, you want those wraparounds. Because after 11 times 3 is 33, you start every 3 times, you kind of get only one extra bit, so it's kind of pretty bad. But and you can see by those plots. So like rotation by 11 or rotation by 1 would be horrible. From this, so hopefully to us it gives us the right intuition what numbers are better than the others. So this is a plot for alpha equals 19. This is a Microsoft choice. Oh boy, I just realized. So I only have, 8 minutes to go? Oh man, that's horrible. So maybe I'll skip one cool topic. I forgot, I saw this as the last topic. But anyway, so let me speed up. So the next permutation, but then we designed this permutation which I can prove both a mathematical result and experimental result. We designed this permutation called bit reverse rotation. We call it Tor. It was like, rotation is rot, and there is some, so anyway, we thought it's a cool name to call it Tor. But yeah, it doesn't have a parameter. And we look at these plots for it, and it's kind of, it's both theoretically good and also practically good. So in principle, if we could implement it in 7 cycles, I think that's what should be used because it has both theoretical guarantee and a practical guarantee, but unfortunately practice wins. So, but anyway, so this is pretty good. So this is a plot for bit reverse rotation. The description is not very hard. It's basically you take a string, you write it in binary, you reverse it, you add 1, and you reverse it back, something like that. So, and if you see, this is how it kind of looks in particular things. And here you can see that if the entropy comes as the least bit, you can see how it travels to these disjoint pieces. So somehow these things, with more pieces, you kind of, in a pretty disjoint way, you can see how we kind of design it. But anyway, so it turns out to be like a pretty cool, it has like nice pictures and things like that. Anyway, so I'll be done. So I only have 7 minutes, but I'll, no, we are not done, but so I'll condense the remaining things. It's hard to condense 20 years of work into even 3 hours, right? So I did the best I could, but I failed. So this is, I'll go quickly just to give you the flavor of these results. So unfortunately, we are not even close. What we want to have to really solve this problem is have your entropy and eat it too. For those who know, there is a saying, I want to have my cake and eat it too. Here we want to do it for entropy, okay? So what is the problem? So the problem is called the technical problem that we are trying to solve is called premature next problem. Okay, so what is the problem? The problem is, so it's like, yeah, the state is compromised, so I have no entropy. And then the entropy comes, so I get this entropic inputs, and I get a little bit of entropy. Then I have a little bit more of entropy. So somehow I kind of accumulate entropy as everything is great, and eventually I have full entropy, and I can apply my Chacha or whatever, some kind of PRG, so everything is great. And so, I'm secure, right? So that's kind of the philosophy. I kind of slowly accumulate entropy, and eventually when it's full, I'm secure. This is our definition so far. The problem that we're dealing is that there is this attacker who is, like, pretty malicious person, but it could be like a user who is like very impatient. So instead of like patiently waiting for the RNG to recover from entropy, there is a little bit of entropy, right? But the attacker is not going to wait until the entropy is full and just say, hey, give me like a RSA key, right? It gets an RSA key with very little entropy. And the problem is, in principle, if this becomes kind of public, effectively this entropy is gone because the attacker can figure out, it looks like there is more entropy, but because you can just look at R and you can do brute force surgeries, maybe a few bits of entropy, you can recover the state. And because the state is recovered effectively, it's like as if you lost all this entropy. You try to do it, you call this premature next, and the entropy is lost. And then you just do, call it again, premature next, the entropy is gone. So how to deal with it? So there are 4 methods how we deal with it. Method number 1 is what I've been talking for the last like almost 3 hours, is don't let the adversary look. So this is our method 1, but here, of course, I'm presenting it in a overly negative way. I still like what I presented to you in the last 3 hours, but basically we are saying, let's replace this attacker from this malicious guy to like a nicer attacker. So this is going to be this guy, like more friendly guy. So basically this guy says, I'm refusing to look, I'm not allowed to challenge until I give enough entropy. So basically it's like you're like super nice and you say, I'm not looking, I'm not calling next, I'm not calling next. And finally the attacker becomes a little bit more powerful, like a little bit friendly and says, okay, now I can look and we are good. All right, so this is kind of essentially our thing. So this is how we defined these conditions, that there has to be enough entropy for extraction condition on the state is equivalent to this thing that the attacker promises not to call premature next. If it does, I'm saying I'm not guaranteeing any security. Of course, you can reverse engineer, but it's still interesting results. But basically, this is what we did so far. So this is our option 1. So we are good. So option 2 is estimate entropy, right? So you can basically say, okay, the attacker is not nice, it's like this malicious guy, and the attacker says, okay, please give me this thing, and I'm saying, oh, not enough entropy, I'm not going to give his output. And this is actually what def-random does. It has this entropy blocking procedure, but of course in our CCS paper, we thought that, this procedure is completely heuristic, it's very easy to kind of fool it. So the problem is, with this so basically you're not giving anything to the attacker if he asks too prematurely, so basically you're putting the, the operating system will estimate entropy, and at the end, you're giving it only when there is enough entropy, and now you're in good. Everything is good, okay? So this is a great solution. In fact, Linux is still using it, even though I think, actually even in the new version, I think they will still use it, despite my protest. But I'm not sure protest. It's a good heuristic, but of course, it's not sound theoretically. The problem is we cannot estimate entropy. I don't know how to estimate entropy, so this is also of limited use, at least if you want to prove stuff. So option 3 is proof impossibility. Okay, so this is option 3. In the past version of this talk in 2014, there was this joke. We said, well, unfortunately, it is possible. So this option doesn't work, but I'm going to say stay tuned. This is the last thing that I'm going to talk in the last 2 minutes. Sorry, I might take like 2 more minutes at the end, but to get you some recent results. So stay tuned for this thing. So proof impossibility, we'll come back to this point. And the last thing is actually what people do in practice in both Windows and Linux is this option is our goal. Eat your entropy and have it too. So this is the philosophy of what we are trying to do. So the way we are going to do, rather than throwing all the entropy into one, it's called pool, into one kind of bucket and waiting until it accumulates, you say, hey, why one? Let's have several pools of entropy. So and when the entropy comes in, there will be some particular procedure. It changes depending on the thing. So he came at the right moment, but so he'll hear the punchline. So we'll decide to say, okay, now this entropy comes to this pool. Next entropy, maybe there is some unknown amount, but I'll just throw it in one pool. Next entropy comes here, and so on, right? And now the attacker maybe this one will be consumed by next. When I call premature next, intuitively I will only consume again in some clever way. I will consume only one of the pools. I'm not going to touch all the pools. I'll consume in some clever way one pool. So in this case here, the attacker basically kills this entropy. But now you see the attacker didn't kill all the entropy because at least this thing is not completely wasted, right? So the philosophy is by spreading entropy in multiple pools and consuming it in a clever way, we are hoping that we are not going to lose all our entropy. That we'll lose a little bit of entropy, and then hopefully I'm kind of fast forwarding. Maybe eventually if the attacker, even though the attacker gets all those things, eventually there will be one thing is full. If the attacker calls next, now it's no longer premature. So basically the attacker is beat up. Okay, so we defeated the attacker. So, right. So our goal is to kind of make sure that eventually, no matter what the attacker does, one pool gets full. Right. So even though the attacker calls next in a crazy way, somehow eventually one pool gets full and is beat up. So this is a paper with Adi Shamir at Crypto14 where we formalize this thing. So anyway, he looks a little bit like Adi, but maybe, I don't know. Itai, don't tell it to Adi, okay? So it's an internal joke. So anyway, so this is, yeah, well, all right. So I'll take I literally have 2 slides to go. So sorry about keeping you a little bit over time, but I'll be done in 2 minutes. So this idea is used in practice, but not in theory. Yarrow uses 2 pools. Fortuna uses more pools. It uses 32 pools, and it has some clever scheduling. So what we did, we basically have 2 papers. A paper in Crypto14 where we showed that this is possible. Is basically we showed that the Fortuna construction, which is what is done here. So the Fortuna construction is seedless, but we can only prove it for this constant rate attacker. So we proved that it's secure, and this is the intuition in the original design. We said that if the entropy comes at a constant rate, I don't know what a constant is, no matter what constant rate it comes, every kind of interrupts give me, I don't know, some fixed amount of entropy. Somehow it kind of works in a provable way, but only for constant rate things. The entropy is not allowed to fluctuate. But also we have a seeded variant of Fortuna, which, as I said, in practice we don't like the seeded things. But in that paper we looked at the seeded version where we choose randomly in a way the attacker doesn't know in advance where I'm going to throw the entropy. Basically, I have some hidden pseudo-random function, and I'm throwing it in a random pool, so the attacker doesn't know which pool is kind of being used. And we showed in a provable way how Fortuna works in this question. And in the recent paper that will appear at ITC this year, unfortunately, we confirmed our intuition that a fully seedless PRNG design, unfortunately, right, because we want a seedless design, unfortunately, is impossible. It's too good to be true. So that was a negative thing. But the positive thing was we did recover some positive result, but we have to introduce a more conservative notion of entropy. I will not have time to tell you what this notion of entropy is, but basically it's a formalization of further restriction on the attacker that entropy is allowed to fluctuate, but not in a too crazy way. So in order to attack this Fortuna thing, you have to give 1 bit of entropy, no entropy for a while, then you have to do this kind of spike. So if things are kind of continuous, we actually show a more general result, a generalization of this concentrate results that Fortuna actually works. So we have both negative and positive results. So I will not have time to show you the impossibility result and the definition. So I have those are the slides that I did at 3 a.m. And I'll just move to the conclusion. But anyway, it's a cute new result. Sorry, I totally forgot about it. Otherwise, I would have moved faster. But yeah, it's cool stuff. I encourage you to read the paper. So anyways, the summary, and I'll conclude. So I think it's I showed this. There are clean theoretical questions with diverse connections. A lot of tools can be used from all kinds of topics. Here, there are really well implications of what we do. Possibly we have a way to influence practical designs. We can combine theory and practice both ways. And the important thing, I think, in practice, on lessons that we learn, the seedless designs are important. So yeah, people don't like the seeded designs because the failures are catastrophic. So still some work remains to be done. But anyway, coming back to the first slide at the beginning, this Smigel guy. So hopefully we at the Smigel time right now. So we, hopefully we'll build a better standard for RNGs and so on. And anyway, I'll stop here.